right, go for it.
Awesome. Well, thank you so much, Allison. Yes, it means a lot. I've been, as Allison mentioned, I've been working in her lab for the last year with focusing on trying to measure the viscosity and conductivity of lithium-doped ionic liquids. That's quite a mouthful, so I'd like to first of all break down each part of this title and kind of go through step by step what we mean. For instance, exactly what we mean by conductivity and viscosity, although probably all of you are familiar with the term, we are specifically looking at the these properties at a molecular level. And when we talk about room temperature or ionic liquids, specifically what is a room temperature ionic liquid, and then when we talk about the effects of lithium salt addition, we're looking at the effects of lithium salt addition specifically on the molecular level properties of viscosity and conductivity. So without further ado, we'll begin by trying to define what viscosity is. We tend to perceive viscosity as being kind of the stickiness and the resistance to flow of a liquid. On a molecular level, we tend to actually think of viscosity as how momentum is transferred in between molecules of a liquid. We know that the viscosity of a liquid is definitely influenced by the amount of intermolecular interactions that go on between the molecules of a liquid. Conductivity, on the other hand, can be thought of on a macro scale as how well a current transfers through or goes through a liquid. On a molecular level, though, we imagine that we look at how well a charge or a charged molecule actually is transferred or moves through a liquid when you apply a potential difference across that liquid. In this little animation, you can see the little plus, it starts moving around, and then it goes and it adjusts to the applied potential difference. What we really want to ask by looking at this talk is what is affecting the conductivity of a liquid? What intermolecular interactions and molecular level properties can affect the conductivity of a solution? And very importantly, how do we model these systems? A room temperature ionic liquid is pretty much, as you might imagine, just a salt that is liquid at a given temperature. We imagine that if we took something like sodium chloride, which is a solid, and heated it up to maybe 1,000 degrees Celsius, that we would actually it would go into the liquid phase. A room temperature ionic liquid, well, it's room temperature at, it's room temperature at, it's a liquid at room temperature caused by having very bulky cations and anions. The reason why we are so interested in looking at room temperature ionic liquids already looking at room temperature ionic liquids is because of their unique physical properties. Room temperature ionic liquids do not have a vapor pressure, they're non-flammable, and because they're just a liquid composed of ions, they're already very conductive. In particular, applications recently have been focusing on trying to make a lithium-ion battery where the solvent for the lithium ions is a room temperature ionic liquid. The idea that being, instead of your Samsung phone exploding randomly due to the vapor pressure and then catching on fire because of the flammability, well, a lithium-ion battery composed of ionic liquids would do none of those things. Lithium addition. Specifically, we're looking at taking lithium addition, we're taking lithium salts and basically just pouring them into room temperature ionic liquids. We know from previous studies done on room temperature ionic liquids with lithium salt addition that the viscosity increases and that the conductivity tends to decrease. What we're really trying to ask is why. And there's two theories of explanation that I've been working with and that I'd like to cover in this talk. One is the standard kind of more canon model, which is hydrodynamic theory, which is related to the ability of these salts to aggregate when in presence of the room temperature ionic liquid. And then the compensated Arrhenius formalism. We're missing a formalism right there. And that the compensated Arrhenius formalism is the technique and model that we've been trying to use to explain this observed increase in viscosity and decrease in conductivity. But first, I'll cover hydrodynamic theory to see the competition we're competing against. So hydrodynamic theory basically describes liquid molecular transport properties as being interrelated. The Stokes-Einstein equation relates diffusion here as being equal to the Boltzmann constant times the temperature divided by 6 times pi times the radius of the molecule, assuming it's spherical, times the viscosity. This means that diffusion, a molecular transport property trying to represent mass transfer in the liquid, is actually dependent upon another macroscale property of viscosity. We can relate conductivity, or in this case molar conductivity, using hydrodynamic theory by relating the diffusion times the diffusion of the cation and the anion times the charge of the ion, the fundamental charge of an electron times Faraday's constant squared divided by the Boltzmann factor times temperature. This means that fundamentally the conductivity is related to the diffusion, which in turn is related to the viscosity. See how we're taking macroscopic properties and trying to continue to explain other macroscopic properties. This means that the conductivity of a liquid inherently is then dependent on its viscosity. So what hydrodynamic theory would say is that this decrease in conductivity that we observe in our room temperature ionic liquids as we add lithium salts to them is caused by an increase in the viscosity. But we have to ask now, how are we increasing the liquid's viscosity? What is causing that according to hydrodynamic theory? This gets us into the topic of aggregation. Aggregation, in its most simple, is really the strong interactions between the anions and cations in a liquid. In the case specifically of our lithium ion, we can imagine that lithium ions can bond to this lithium cations can bond, or not bond physically, but very strongly intermolecularly interact with our associated anion here. And they can interact in a number of different ways as outlined by, as you can see in this particular diagram. The increased mass caused by the aggregation of lithium, since it's such a charged and small ion, causes the observed increase in viscosity. Basically, we have a larger molecule because it's aggregated, and it's harder to move that through a liquid because it's so much more mass. That's hydrodynamic theory's explanation for our observation in the increase in viscosity. And as we can see, as we increase in viscosity, and if we go briefly back to the other slide, as we increase viscosity, we decrease the diffusion, and a decrease in the diffusion for both the cation and the anion will result in a decrease in the conductivity. But now, turning away from hydrodynamic theory, we'll continue on into now understanding the compensated Arrhenius formalism. At its heart, the compensated Arrhenius formalism is a modified transition state theory. The idea being that if we want to represent how molecules move through a liquid, that we have to understand it via overcoming intermolecular interactions that keep it in place. We imagine that this red molecule here is the molecule of interest that we're looking at, and that these dashed lines are the intermolecular interactions that it's having with other molecules nearby. In order to move, it's going to need to break these molecular interactions. This corresponds to an potential energy high point, known as the transition state. This transition state requires a certain amount of energy to be reached. This energy is known as the activation energy. The molecule will then either go back to its original state or move and then reform its intermolecular interactions, resulting back into an energy low. Not only is the compensated Arrhenius formalism a modified transition state theory, but the first postulate of the CAF assumes that molecular transport properties such as conductivity, diffusion, and fluidity, which is the inverse of viscosity, so that's a little bit harder to keep track of, can be represented with an Arrhenius-like expression, where we have, in this case, the fluidity, the inverse of viscosity, equal to an exponential prefactor times e to the negative EA RT. We imagine that not only can fluidity be represented as this in this Arrhenius form, but also the conductivity and the diffusion. Now that we have this general form, we know what makes this in particular a compensated Arrhenius formalism, whereas this is a simple Arrhenius formalism, where that we suppose, with the second postulate of the CAF, that the temperature dependence of the exponential prefactor, which in this case is the sigma naught, is entirely due to the dielectric constants of the material's temperature dependence. That's a mouthful. That's why I have a little bit that goes down here. So we imagine that the exponential prefactor is temperature's dependence is completely due to the dielectric's temperature dependence, just to reiterate. So you may be asking to yourself, what exactly is a dielectric constant? What does this mean? And why should it relate to our molecular transport properties such as viscosity, or fluidity, conductivity, and diffusion? So I'll take a brief moment to talk about the dielectric constant and exactly what it means. Imagine that our liquid is composed of a sea of dipoles. When we apply an external electric field, these dipoles will orient to that electric field, as you can see here. We have to wonder what affects the dipole's ability to orient to this new electric field. It's the strength of the intermolecular interactions already present between the different dipoles, and then the effectiveness of the local electric field. The effectiveness of the electric field in the local environment. Well, what exactly do we mean by that? When we apply an external electric field, the molecules begin to orient. And because all these dipoles are oriented in the same way, an electric field is generated by those dipoles, called the dielectric electric field, because it is a dielectric electric field. This dielectric electric field is usually small in comparison to the external electric field, but because all the dipoles are oriented in the same pattern, when you apply the external electric field, that means that you now magnify and kind of allow for the dielectric electric fields to compound upon each other. Because of the way the dipoles orient, we know that the dielectric electric field is going to be in the opposite direction of the external electric field. Now, why does this matter if the dielectric electric field is so small? Well, if we're dealing with a sea of dipoles, because that's what most liquids are, we imagine that any given dipole within the sea of dipoles is going to be affected significantly by the other dipoles around it. Now, if they're all oriented to an electric field, we imagine that the effective electric field felt by a particular dipole is going to be heavily dependent not only upon the external electric field, but also its surrounding dielectric electric field. This is how the dielectric constant fits in. The dielectric constant is the relationship between the electric field of the dielectric, so the molecules, the dipoles surrounding it generate electric field, and the electric field in a vacuum. But what you may be asking is that how is this dielectric field temperature dependent? Well, here we can imagine that we have a molecule of interest, our dipole of interest, that's surrounded by four nearby dipoles that are generating their own electric fields, dielectric electric fields. As we increase the temperature, these dipoles get further and further away from each other, and therefore they are less effective in interacting with this molecule, with this dipole. This relates back, this idea means that because we have less dipoles in a given volume, or the dipole density, if you will, of that given volume has decreased, therefore we'd expect the electric field, the dielectric electric field to also decrease. So with increasing temperature, we note that the dielectric constant goes down, and then we can imagine if we went in the reverse and cooled it down quite a bit, the dielectric constant, because of these close interactions with these other molecules next to it, increases as the dipole density increases itself. Slight problem though. The dielectric constant itself is a macro scale property. We usually associate the dielectric constant with being the overall effectiveness of a material, or the dielectric field of an entire material. And the second problem we have is, and therefore it's hard to understand the dielectric electric field's effects on molecular level transport properties. The other problem we have is that we cannot measure the dielectric constant of room temperature ionic liquids with our given equipment. Our impedance analyzer only goes up to a high enough frequency, and it is not sufficient to reach to then calculate the dielectric constant of room temperature ionic liquids. But back to the original problem. How can we understand what the CAF is telling us using the dielectric constant, which is a macro scale property, without, how can we understand how what the CF is talking about on a molecular level if we're using macro scale properties? So what we'd like to do is relate the dielectric constant to a more molecular level property of a given material. In Petrowski et al. 2012, which was research done by Allison and her group back at Oklahoma, they related the dipole density of a material to its dielectric constant using Onsager's model. This allows us now to go back and be able to relate a molecular level property as causing these difference and variations in molecular level transport properties in liquids. So I'm going to now talk about what exactly Onsager's model and how exactly they did that. This by itself is Onsager's model. The epsilon sub s being the dielectric constant, the epsilon sub infinity being the high frequency part of the real dielectric constant, being equal to 4 pi times the dipole density times the dipole moment squared divided by 9 Boltzmann constants times temperature. If we do make the assumption that the dielectric constant is significantly larger than the high frequency part of the real dielectric constant, we can come down to this statement saying that the dielectric constant is approximately equal to the dipole density times divided by temperature times a bunch of these constants that we have here. This assumption was verified for polar organic liquids by Petrowski et al. In the scope of that paper that made the original assumption. But how exactly can we use this then? Because we know this to be true, we know that the dielectric constant is proportional to the dipole density divided by temperature. In order to clarify exactly what I mean by dipole density, I'm going to give a brief illustration. The dipole density itself equals the number of dipoles per unit volume. If we imagine this over here being a given volume of a liquid at a normal temperature here, then we would imagine the number of dipoles within this unit volume is the molecule's dipole density. As we increase the temperature, we imagine that the number of dipoles per unit volume also decreases. This is the temperature dependence of the dipole density. Now we can take our original compensated Arrhenius formulism and transform it as being dependent, the exponential B factor being dependent on the temperature dependence of the dielectric constant and turn it into, using Onsager's model, a new version of the compensated radius formulas where we now relate the exponential prefactor as being dependent on the dipole density divided by the temperature. So how do we determine n? Why is this significantly better for us? Well, the dipole density itself is just pretty much equal to the density divided by the molar mass. If you think about this, we're basically saying that the amount of molecules, we are basically just determining the amount of molecules per given volume, and therefore, if we assume that there is one dipole per molecule, therefore we have how many dipoles there are per unit volume. This allows us to completely bypass determining a material's dielectric constant, and it's proven very useful in studying room temperature ionic liquids in the last couple of years for Allison's research group. Now I'd like to move into specifically what my system was and what we were exactly looking for. So I'll begin by describing my ionic liquid that I was working with. I worked with an N-alkyl N-methylpyrrolidinium based cation, this guy over here, and bis-trifluorosulfonamide cation, or anion, sorry, I might have flipped those. We chose to use 4 different ionic liquids. In this case, we varied the difference between the 4 being the length of the alkyl chain within the cation of our ionic liquids. One of those was being the propyl cation, the next one being the butyl, the next one being the hexyl, and the fourth one being the octyl. We chose our lithium salt to be lithium bis-trifluorosulfonamide, or lithium TFSI, in which to dope into our room temperature ionic liquid. In particular, we chose the system because the room temperature ionic liquid, in particular that we're looking at, the pyrrolidinium-based cation, had a very high solubility for lithium TFSI. We also chose to use the same anion for both the salt and the room temperature ionic liquid in order to specifically study how the lithium ion affected our conductivity and viscosity. We eliminate variables by using the same anion in both the salt and room temperature ionic liquid. And lastly, why try TFSI? Well, TFSI has the capability of being used for spectroscopic analysis, for understanding how exactly the lithiums are coordinating in liquid phase to, in this case, the TFSI anion. This is not work we're doing here, but are collaborating with other groups around the country that Allison is working with in order to hopefully better understand the system and its molecular transport properties. I'd like next to go through and talk about how we use the CIF. We now know how we use the CIF. We've got a couple of variables here to deal with. We've got the dipole density here, and we've got the activation energy here. In order to solve for this, we need to somehow vary the dipole density and vary the temperature. Well, it's very easy to vary temperature. We do a 5 to 85 degrees Celsius range. But in order to vary dipole density, we use these 4 different cations with varying alkyl chain length. The idea being that as we add members onto the alkyl chain length, the molecules themselves in a liquid have to be further apart from each other, thus varying the amount of dipoles that exist per unit volume. Using this, we were able to collect data for all 4 different room temperature ionic liquids doped with lithium salts. This specific plot here shows the dipole density as a function of temperature divided by temperature on the x-axis here, and the fluidity, inverse viscosity, on the y-axis. Now, you can see here that on the right, we have a temperature scale here, where the darker colors associate with lower temperature, 5 degrees Celsius, and as we get warmer, we are going up to higher temperatures, 85 degrees Celsius. And that for each individual series, we take the temperature and we take the fluidity and the density of the solution at each individual point. In that way, we are able to calculate the dipole density, which is the x-axis. From there, now that we have the data for each individual room temperature ionic liquid, we were able to use a method called the scaling procedure in order to cancel out the exponential prefactor. By canceling out the exponential prefactor by using a temperature reference curve, in this case 55 degrees Celsius, and we're solving for the C6 end member, we are able to then solve for the activation energy by itself. Once we solve for the activation energy by itself, we are then able to determine the value of the exponential prefactor. Before I get into the results of our data for in this case, fluidity, I want to talk about what we would have expected to see using the CAF. Upon lithium addition, we expected that the activation energy was going to increase. This, if you remember this image from earlier, basically we were saying that it would take more energy to surmount to get into the transition state. Why? Because we expected the strength of the intermolecular interactions upon the addition of lithium for our liquid to also increase. Because lithium is a very small and very charged ion. Therefore, its intermolecular interactions would be more likely to be significantly stronger than our big, bulky, room temperature ionic liquid cation. So we imagine as we replace more of our solution with lithium and make it more, replace more of our solution with lithium, therefore we are increasing the overall amount of strong intermolecular interactions, therefore making it harder for that liquid overall to move through the fluid. What we actually found. For fluidity, which is the data we do have, the neat RTIL, so basically the non-lithium room temperature ionic liquid, had an activation energy of 42.3 kilojoules. In comparison, the lithium-doped room temperature ionic liquid had an EA of 44.2. This is not significant, that's not very different, and does not necessarily explain why we see a dramatic shift in conductivity and viscosity, or in this case, fluidity, for our room temperature ionic liquids between the lithium and non-lithium samples. So we have to ask what could explain this. Well, if we go back to our equation, which I've been told is what we should be doing always when we run into a problem, we imagine that if the EA is not changing significantly, well, the only thing left to change is the exponential prefactor. This means that the difference between the viscosity of our solutions is caused by a change in the exponential prefactor. We don't necessarily know exactly what that means on a molecular level, and Allison is working on a theory paper to hopefully explain some of those nuances in the near future. But what I'd like to continue doing, and hope that will be continued to be done, is we should eventually obtain conductivity data for our lithium-doped room temperature ionic liquids in order to compare to our non-lithium doped, and basically do the same thing that we did for fluidity, but with conductivity. We also want to take a brief moment to verify the water concentration of our room temperature ionic liquids, because if there's significant amounts of water in our room temperature ionic liquids, we imagine that that can influence the molecular transport properties. We also hope to try new concentrations to see how the concentration of lithium salt affects these physical properties, and hopefully kind of deduce out what's exactly going on upon different amounts of lithium salt doping. I would like to acknowledge the entire Lawrence University Chemistry Department for helping me at all stages, if nothing else, with my chemistry education here, which to say that it makes it seem like it's a minor thing. But also, and especially, I'd like to thank Professor Fleshman, who brought me onto this project, and me and her really worked together to develop it and come up with the ideas behind it. And I can't say how much that I can't express my gratitude enough for that. I would also like to thank Augustus Lowry because the data collected for the non-lithium dope samples is actually his and he collected it. Wesley Hesher for allowing me to bounce ideas off of him and being a good person to talk to when Allison was busy about what was going on with the system. And Daniel Martin for tirelessly being able to help me with all my mechanical issues and material needs. Thank you. Okay. Yes, Wesley. Yes.
So you're doping lithium into the ionic liquids. Wouldn't that effectively decrease the dipole density? Could that be an explanation for what's going on in the prefactor there?
That's a possibility. Yeah. I mean, if if we're the dipole density. Let me think about it for a little bit. Maybe I'll get back to you. Don't want to be presumptuous.
Can I?
Yeah.
Cool.
You're allowed.
So one of the hardest parts of using the dipole density model with ionic liquids is to know how can we make the assumption, or can we make the assumption that there's one dipole per salt molecule that you put in, because you got the cation and the counter anion. And so we're making the somewhat, would you say, bad assumption at this point, that you get one dipole per salt that you put in. And so with the lithium, we don't know how those dipoles change. So quantifying what is actually a dipole for an ionic liquid is a very hard problem. And we don't know how to do it. So we're just making a bad assumption across the board, and we're hoping we see some trends.
Right?
Right.
That point to maybe what assumptions we should be making.
Right.
Yep. Okay. Any other questions?
So you said that the kind of 2 kilojoules increase in activation energy was not enough. How big would you need that increase to be in order to account for the macro scale properties that you are seeing?
I'm sure that's kind of a neat calculation we could do. Apparently 5 is around what we're looking for.
Okay.
But I would imagine just...
So we're just under half.
Yeah, and what I would say is that when I was doing the CIF analysis, sometimes for each individual family member or each individual alkyl chain length, room temperature ionic liquid, we usually see a variation of about 1 kilojoule just because of what we would consider some calculation error. Yeah, so I didn't want to use the word significantly different because that would be a little bit presumptuous, but we'd expect a larger difference between the two. Okay. Wesley?
Well, when you're doping specifically the lithium TFSI, if you were to select a different anion, I mean, does the exact identity of the anion, need it be identical to whatever it is you're doping it into?
Yeah, so the reason why we chose to use the same anion is because we were hoping to see exactly what the lithium does, how the lithium changes the activation energy or the exponential prefactor. The idea being that if we use, let's say, chloride or something like that, that we now have to start accounting for what chloride's doing by interacting with the cation or anything else. So that's the hope. Is that a good answer for you, or is that okay?
Add on to something as well.
Yes.
So one of the other problems with these ionic liquids, if you get the anion too small, then they start to solidify, and they're no longer liquid at room temperature, especially when we go down in some of the temperatures. And so if you were to add a chlorine, then you have now you've got competing salts formation, and you would no longer be in the liquid phase. And so we're constantly combating against that.
I spent many a late night looking at the viscometer, trying to decide if it was solidifying or not, and if I should stop the experiment. So that's, you definitely run on the edge of that temperature range right there. Erica.
How does the viscometer measure viscosity?
I'm glad you asked. Okay. We use a falling ball method with attachment to a piece of equipment we got from Anton Parr. So the falling ball idea is that we have a known we have a capillary that has a known width within it, and that we fill the fluid inside here, and then we let gravity take a small steel ball and fall through that fluid. And that allows us to determine the viscosity from there, because we know the balls are very specially engineered to be the right mass and the right shape, and the capillaries are very expensive to be exactly the right width. Cheers.
How big is this capillary? Like the little ball? Oh.
1.8 millimeters.
1.8 millimeters. Yeah.
It's
Okay,
thin.
that's-
Yeah,
It's
the
about
balls.
this long, but it's very thin.
I probably shouldn't admit this, but they're very easy to lose. They're very small. And then there's a lot of them. Don't get too worried.
Not infinite numbers.
I know.
The balls are
Oh.
not
What was this project seems to have a lot of moving parts and a lot of new
Yeah.
research associated with it. What was the hardest part for you? What was the most fun part for you?
Of my overall
Yeah,
experience.
the whole project.
Oh, the whole project. I would say some of the most fun I would definitely say was working in the lab for me. I really enjoyed kind of fiddling with things and trying to get them to work, or like being like, oh, that data doesn't look right, you know what I mean? And kind of that very hands-on approach. Sometimes the things that I didn't enjoy were reading through papers and trying to glean out exactly the its and bits details and the very nuanced language. So I would say reading through the scientific literature was always a little
Lots
bit
of
of a chore.
nuances in this stuff.
Yes, yeah, and I know that Allison constantly went through the same material over and over again, trying to get me to understand how the dielectric constant relates to this.
Lots and lots of nuances.
Yeah.
Thank you.
Any other questions, or shall we? Hooray to the CAF and Chris. So again, for those of you who are just so, like I said, we don't have any more CAF talks.
No.
But we do have some really cool other talks that are happening on Wednesday at 3:10 and 4:30, and then on Friday, 3:10 and 4 o'clock. Don't forget, we have our chemistry picnic, 4:30 on Thursday. And that's all we have for you today. So thank you so much for coming.
Yay.
Do I get an applause?
Did you take attendance?